As I get started here, can I get a show of hands? How many people have had a chance to see the movie Project Hail Mary? A few. So it's actually an environmental parable. I urge people to go see it and remember that the theme of the book by Andy Weir and the movie is solving a cosmic environmental problem. Fortunately, we've got something more local we're working on. And the other movie you may have seen is Apollo 13 with Tom Hanks. Show of hands. Oh, that's a few more. One of the favorite lines I know from that movie is, "Failure is not an option." And I've got that button, and it's a reminder that this is serious. So I'm going to see if I can get my slides working here with this. Okay. I'm going to tell you about some of the technology we're working on in support of climate restoration. And I'll be interested to hear your questions and see how I can help clarify things. Green button. Tell me what I'm doing wrong. Okay. So, in a nutshell, to take nothing else away, we are working on a system to measure carbon dioxide removal in marine carbon dioxide removal projects. This is some work I'll tell you about in a little bit that we did working with our sensors. Now, you may have, back in high school or college, seen pictures of the carbon cycle. And I'm not going to go into the depths of this, but the important thing is we're focused on what's happening in the ocean. You saw this a little earlier, but just as a reminder, this is known as the Keeling curve. It's measurement of carbon dioxide in the atmosphere at the Mauna Loa NOAA measurement station. Scientist Keeling founded this in 1958. That's the beginning, back around 300 parts per million back in mid-20th century, up to 420 parts per million now, which we've had explained to us is about 1,000 gigatons of excess carbon dioxide in the air. Now, there's lots of models about how this all works, and I'm not going to work through all of those. There are atmospheric scientists and marine biologists who've been studying this stuff for a long time, and a lot of it's understood and a lot of it still needs research. But what we can understand, and it's pretty clear, is carbon dioxide does dissolve into the ocean, causes ocean acidification, and balances out what's in the air. But some of it comes back out. It's a dynamic system. And phytoplankton, as has been mentioned, are in the ocean. They are plants that do photosynthesis. They grab some of that carbon dioxide, and some of that stays in the ocean, and that's a good thing. But in these projects, we need to measure what's going on in the air and the water to understand the effectiveness. So, just to review, phytoplankton growth is the most promising way to reverse global warming. The phytoplankton is the foundation of the food chain. They consume the carbon dioxide. Some of that stays in the ocean a very long time. A scientist, an oceanographer by the name of J.H. Martin, did the research a couple of decades ago explaining that dust storms and volcanoes deposit a lot of iron-containing dust in the ocean, and that's when you get phytoplankton blooms. And of course, we can replicate that process. Excuse me. So our project, our team is not working on all aspects of the whole problem of how to conduct this project, this process. For example, we're not going to be working on how to prove the sequestration of carbon in the ocean. It's something that's fairly well understood and still being researched, but the basic idea is that the deeper the carbon goes, the longer it stays in the ocean. And I'm relying on other experts, marine biologists, to continue to do that research. But what we're working on is the idea of, if you put small amounts of iron in the ocean, in some select areas around the ocean, can you get the desired effect? So research is needed. And there are two things that we're trying to get at with this research. One is the effectiveness of the process. Is it really doing what we believe? And second of all, safety. And that means, are there any ecological impacts that are of concern? Now, there have been 12 or 13 field trials around the planet doing this sort of work, and there's been a lot of speculation about ecological impacts, but I don't think anything serious has been reported. So we are optimistic that this is really the way to go. So here's the project that is and I will mention, you know, I learned about this initially having met Peter about 1.5 years ago and having read the climate restoration book. And so the basic idea here that we've been discussing is, you start off with a ship distributing small amounts of iron and repeatedly in a project area, a localized area, and that stimulates the phytoplankton to grow. Nitrogen fixing, there's a tongue twister. Organisms grow, helping to sustain the phytoplankton. This is part of the whole marine biology that needs to, is understood and needs to be further confirmed. And some of that carbon goes deep in the ocean. Now, we are working on, and this is what I'll talk about a little further as we go on, a way of measuring how much carbon dioxide is actually being removed from the atmosphere. We use some sensors on buoys and transmit that data to satellites so that we can get that remotely. And we also will use some sensors on drone vessels to monitor a variety of parameters, because we're measuring not just effectiveness, but also potential ecological impacts. And there is something called the NASA Orbiting Carbon Observatory 2 satellite, which is providing a lot of information about surface level carbon dioxide levels. It's done with spectrography, and it goes around the planet and repeatedly measures different areas. It's not a constant thing, though, so we need to measure locally as well as with the satellite. So here's some information about the devices that we are developing. On the left, you see a SOFAR spotter buoy. These are commercially available. They are about $10,000 a piece. They're about 16 inches in diameter. And microelectronics have really made it possible for us to do a lot of things today. These buoys are typically deployed in the ocean for measuring wind and wave action, and it's used in the shipping industry. And you can see solar panels on the side, and they have GPS and satellite radio communication to transmit the data. And they have a way to connect other sensors. So our early prototype, shown in the middle, had some sensors in a PVC arrangement to measure carbon dioxide in the air. And our more recent version on the right side has, in that column atop it, a sensor that's going to measure the carbon dioxide in the air. So the monitoring calculations are fairly straightforward. You measure carbon dioxide in a buoy that's in the upwind region of where your project area is, where you're doing the iron fertilization. And then you measure downwind, and you calculate the difference, see what the effect is. And you integrate across a network of buoys to see what's going on in the area. So recently we did some testing in San Francisco Bay. This is our crew. Marcos was part of the team out in the bay. And what we were testing is keeping the buoys moving with the current. And so some of these buoys have different configurations of drogue chutes on them to make sure they stay with the deep water that's the current is moving. And this was done in, if you know the San Francisco Bay Area, it's called Raccoon Straits between Tiburon and Angel Island. And when the tides happen, you get sort of a really strong movement through there. We're calling the system COBALT, the Carbon Ocean-Based Atmospheric Link Telemetry, and it's under development. We feel pretty confident that it's going to be giving us some useful information. We need to do some more testing in the ocean. It's one thing to test in the fairly calm waters of San Francisco Bay. We need to get out in the deep water and do some more testing. And of course, we're going to coordinate with the satellite monitoring information that our team has been analyzing. So the main thing I really am here today to talk to you about is our status as a nonprofit. We need your help. And I've shared some of the cards with our website information. We are a nonprofit dedicated to moving this technology forward. And we know that this technology is not something we can implement with our small Deep Green Solutions crew. We know that we're going to need to hand this off to others around the world, and they will be able to deploy this more widely. And the quantity, this is just an example for conceptual, it's not specific locations, but the idea is that you do this in small areas around the world in the ocean, and enough to do the desired effect. And as Peter's book has explained, the idea is to remove 1,000 gigatons of carbon dioxide from the atmosphere in the time frame of 2030 to 2050. We've got to get started. Our team is a powerful one. Tan is our CEO. He's an electrical engineer who's also worked in the climate space. I'm a registered civil engineer in California, did a couple of decades of environmental engineering. Alan is a PhD physical chemist who recently retired from Lawrence Livermore National Lab. And he's been helping us with a lot of the calculations. Our hardware and software guy is Joe Brabeck, excuse me, who recently retired from Topcon, which is another technology company in Silicon Valley that has made positioning information technology in the agriculture space. Marcus, you've met. He's an ex-Navy guy. I don't know if everybody here knows, but he was an air traffic controller in the Navy and did a lot of logistics work. And logistics is a big component of what we have here. And of course, you heard from Carol this morning, who co-authored the book on climate restoration, and she's also a member of our board. So we've accomplished a fair amount in the 1 year. It's just coming up in a week or two on the anniversary of forming our 501c3 nonprofit. We continued testing with the CO2 sensors on the buoys. Alan and Joe have developed an algorithm and worked with Peter on the algorithm for analyzing NASA satellite data analysis. We produced some papers on the underlying science. I gave a talk exactly 1 year ago at an IEEE conference, the Institute for Electrical and Electronic Engineers, at their Sustainability Technology Conference in Southern California. That's why I couldn't be here at EarthX last year, but it was very successful in that someone in the audience was able to say that he would put a significant contribution in, and he donated enough to really help us get our website started and further the work on developing these buoys. So we've met with the EPA staff. We understand what their EPA permit requirements are under the Marine Protection, Research and Sanctuaries Act of 1972. They are the organization that implements what's known as the London Convention and London Protocol. This was something that's set up in the maritime industry globally to prevent ocean dumping. Some of you may remember that back in the day, several decades ago, they would take barges of garbage out in the ocean and dump them. And the London Convention and London Protocol said, no more dumping. Well, the way the language was written, it actually is so broad that it encompasses depositing tiny amounts of iron in the ocean. And so we have to adhere to these requirements. And right now, the protocols and the way the EPA is implementing it say it's okay to do scientific research right now. So we do these small projects to gather the data that we need to show that this can be not only an effective method of removing carbon dioxide, which is what we want to measure with these buoys, but also that it is a safe practice, which is going to require a lot of money for ecological monitoring equipment on research vessels. Last September, we exhibited at a conference called Oceans 2025, and that was in Chicago. And in September this year, we'll go down to Monterey, California for Oceans 2026, if you're out that way. And we really appreciate the over $100,000 in donations we have received so far. And if you go to our website, there is an easy way to contribute online. So why do we need more money at this time specifically? We need to continue to refine the buoys. They're pretty far along right now, but there's some verification, some calibration that we're striving to do, and making sure that when we deploy them in the ocean, we know how they're going to work. And that it's going to cost some money to get those research vessels out there to do the equipment testing. And we're also working on, we have an outline for the EPA permit. And the good news is a couple of things. The EPA has issued permits for other experiments in the ocean under the MPRSA regulations. Woods Hole Oceanographic Institute on the East Coast recently did an experiment with what's called ocean alkalinity enhancement, where they put limestone dust in the ocean, seeking to change the pH balance and cause carbon dioxide removal that way. That was done last August, and we should be seeing reports published out of what their study is, and that should be very interesting. So there is a path forward to getting an EPA permit, and like I said, we've had conversations with them, and it's going to take some money to refine that permit application. It needs to be carefully documented. As explained, you have to footnote in all your references. We think field trial next year is possible. Money is what it takes to drive this engine. And then after that is the whole thing of scaling up, which is getting other groups involved to pick up on this. And I'm encouraged that even in the time that I've been involved in this in the past year and a half or so, that in the whole marine biology and ocean research community, there's increasingly positive talk about the approach to using phytoplankton-based carbon dioxide removal as the foundation of removing carbon dioxide from the atmosphere. There were more expressions of doubt a few years ago. We're seeing more and more reputable scientists say, this deserves some serious consideration. So I think something we can probably all agree on in this room is we all want to make a difference. And we all enjoy being a part of something. And we care about what happens to our world and to each other. You can be a part of this project. You've got the information in your hands now with those little cards, and we would really appreciate your help. Well, certainly you can read more on our website, a little more detail, and there's some the articles and so forth and references. You can read more about it. you can make a charitable contribution, which would be really appreciated. You can tell your friends and family about climate restoration. Tell them what you heard today. And we could appreciate some skilled help. For example, marine biologist. We don't have one actually on our board right now. We need a marine biology advisor who's going to spend a little bit more time with us to be able to answer some of the specific questions in the design of these studies. Oceanography, another component. There's so many components to this: marine biology, oceanography, meteorology, biochemistry. I've got another slide that I use sometimes, and I say, you know what? It's carbonology. And of course, there's the data analysis part. So if there's computer scientists among you, it's another part of what we're working on. Or you may have other ideas how you'd like to participate. We'd love to hear from you. So it takes a village, and I think we will wrap it up with the statement that the greatest failure of all is the failure to act when action is needed. So thank you for listening.
And then a change of format, David and I are both going to take questions.
And we'll need the microphone. We need the microphone over there.
Fascinating question. Mechanical sequestration right now is $1,000 a ton, which is $37 trillion a year just to keep up with current emissions, not to lower anything. So clearly, it's a myth that that's going to work. Do you have any sense of what this might scale up to be as far as the cost per ton to remove carbon?
I'm going to quote some numbers that I have heard, but I haven't been able to research myself. So you can treat these as hearsay, but I'm going to put it in perspective. Let me first explain something that I heard about COP29 and COP30. The Council of the Parties meetings that have been held annually for a while, in which the less developed countries were asking, and I'll get to the answer to this in a minute, but I need to set the stage. The less developed countries were saying, we're suffering a lot of environmental impact and economic dislocation from climate change. And we'd like the more developed countries to contribute to mitigating these problems. And they estimated that they asked for $1.3 trillion per year to mitigate the impact of climate change. There was some negotiation. I think a number was published of $330 billion per year that would be transferred from more developed countries to less developed countries. I don't know anything about how successful, whether that's actually happening, but it was talked about at COP29 and COP30. But the interesting point about that really struck me is that someone has put a price tag on climate change. It's $1 trillion a year. So when you look at what it's going to take to remove 1,000 gigatons of carbon dioxide from the atmosphere over the period of, say, 2030 to 2050, say at about a rate about 60 gigatons a year, how many billions of dollars or millions of dollars is it going to take? I've heard some estimates that it could be $500 million to $1 billion a year to do this. Now, for those who aren't doing the math in their heads and moving the decimal points around, 1 trillion in annual damage, 1 billion to work on fixing the problem. That's a 1,000 to 1 ratio. So I don't know the exact per ton number. That's the research that is still undergoing. But the general idea is that it is very cost effective compared to the problem that we have. Next.
Just in looking at this whole process, it looked like the potential release of methane and hydrogen sulfide is a concern with carbon sinking. Is that something that you would also be able to monitor with all this, or is that even not really a concern, I guess, with, because I know some people said it's negligible.
That's more of a marine biology question that I'm not equipped to really answer. And I'm reminded the first public technical presentation I ever made was on the water use in electric power generation. And then somebody asked me a thermodynamics question, and I really stumbled on it. And I'm not going to fall into that trap again. I think we can talk later and see if we can find you the reference on that. Maybe Marcus knows off the top of his head.
Yes. There's actually the work of a man it's called the Helmholtz Institute. It's over in Germany. Professor Dr. Victor Smedicek. So Professor Dr. Smedicek has written extensively. He's done about a half dozen ocean fertilization experiments, and you can read specifically about the decomposition effects. And I'm not going to go out on a limb and say it's negligible because this guy is Professor Doctor. I'm Mr. So yeah, if you're interested in it, you can read his research, and it's very enlightening. It assuaged some of my doubts about the safety of ocean iron fertilization, and I believe it'll do yours as well. He's done a lot of writing, and he's also really accessible via email. Professor Dr. Victor Smedicek.
And this is why we work so well together, because he reads a lot.
Is that, with your monitors though, for carbon dioxide, is that something you could also put on other sensors to check the release of other gases?
It's going to be necessary, and that's one of the things I mentioned on one of the slides is the idea of using some drone vessels for doing some of the monitoring. And there's some new ones coming out. Happy to talk to you a little bit more about some of the ideas that are going on there. But there's a whole suite of measurements that marine biologists want to know about in order to evaluate potential ecological impacts, as well as the effectiveness. And we also, we'll want to measure carbon dioxide in the water as opposed to in the air and see what that dynamic relationship is going on, because it's constantly changing.
Excuse me. Greetings. Taking the geographer's eye view of your presentation had two maps that showed access points for observations, whatever. One had 13 points and one had 15 points, and the one with 13 had 7 in the southern hemisphere, and the one with 15 had 8 in the southern hemisphere. My question is there something inherently different about the Southern Ocean that would require more observation, or is it simply there's more ocean in the southern hemisphere?
Okay, to differentiate between the two ones, the first map slide showed where there have been field trials by others. Okay, so those are actual locations. The second one, there's a footnote that says these are just for illustration purposes. The idea, trying to get across the point that we're not doing this across the whole ocean, you do it in tiny specific areas. Now, maybe Marcus can comment on some of the stuff he's read about. There's been a lot of, and I think it was mentioned earlier, the idea of measuring in places that are high nutrient, low chlorophyll, and so forth, and the Southern Ocean gets mentioned a lot, meaning around the Antarctic.
Yes,
Yes,
I do. So the Southern Ocean is where a lot of research is done just because there's no countries near the Southern Ocean. If you're going to do research in the ocean, you don't want to get in the way of whaling fleets, you don't want to get in the way of the Navy, you don't want to get in anybody's way because you're putting things in the water, you're watching them, you're staying on station. So the Southern Ocean is where a lot of research is done, but also the Southern Ocean is where we've lost a lot of ocean biomass via whaling. So I think the statistic was something like whales eat currently, in the 1800s, early 1800s, whales ate annually more krill than there is in the Southern Ocean right now. So when we look at biosphere restoration, the most dramatic effects, the most bang for your buck, a lot of people believe it will be in the Southern Ocean. And whether or not that's true, that's where a lot of the research is. So that's why when you look at when you talk to any oceanographers, they're like, we were in Antarctica, it was negative 15 degrees Celsius. And that's why. That's where all the research is done.
And you'll hear more from one of our speakers this afternoon about some of the research going on about the Southern Ocean.
Right. Anybody else?
Hard to see who else? That's right. I'm what stands between you and lunch, so. We'll be around today if you want to ask questions, and of course, we may not have all the answers today, but we can certainly follow up.
And I do have one more piece of help that we need. If you are very social media savvy, if you are good at the internet or art or drawing or anything creative, we would love that. I'm on the comms team, and I can't do anything artistic. I named my son Marcus, and my name's Marcus. I'm not good at this type of thing. We need you.
He claims he's not creative, but he's really an inspiration. So thank you, Marcus.
Thank you.
I have a question about the relative masses of things that people are putting in the ocean. So the Scripps Institute did this big alkalinity experiment. They would put sodium hydroxide lie in the ocean, right?
Yeah.
And how many tons of that did they do in this demonstration thing, and how many tons of iron are being proposed, or iron per?
I don't have
square
the
mile?
tonnage off the top of my head. I'll quote something I do remember from J.H. Martin, the oceanographer who did a lot of the early research on the effects of iron on phytoplankton growth. And I believe, and correct me if I'm wrong, folks, he said something along, give me a tanker of iron dust in the ocean and I'll give you an ice age.
Right, because that would create so much cooling.
So remember, the ocean is 71% of the planet. A one tanker, you can hardly find it in the ocean. It's tiny amounts, and we can get you the actual calculation numbers later.
I got
It sounds
you.
like Ray might have some information about this as well. Yeah.
Yeah, so Loch Ness, the most recent ocean alkalinity enhancement experiment,
Right.
put 20 metric tons of lye into the ocean. Well, not lye, sodium hydroxide into the ocean.
Drano. Fine, and I don't have a problem with it. I'm just kind of wondering in terms of an EPA permit. The EPA said, "Oh, you're dumping." Well, who's dumping how much what? And maybe Ray has more information about that. Or
No, I've got it.
Yeah.
oh, okay, great.
No, the EPA permit that Woods Hole got for the
Yeah.
Loch Ness experiment
Right.
it's called ocean alkalinity enhancement.
Right.
They were very specific, and they did a lot of background research. They traced where that material moved with a rhodamine dye that turns pink, and they sailed along and followed where it was dispersing. So they've got some stuff on the Woods Hole website, I think, about what their project was, and they should be publishing a report on the results coming up this year.
I guess my point is that the relative quantities are such that it should be easy to demonstrate to the EPA that the amount of iron that wants to be dispersed as this is implemented or experimented with is an acceptably low number to be set.
It's not the amount, it's not the quantity they're concerned about, it's the effect.
Yeah.
So what happens when phytoplankton grow? There is speculation of other ecological impacts of disturbing the habitat, and we have to say that it's speculation, and we need the research to find out what really happens when you do this at scale.
And we want to remember that when we talk about dealing with the EPA, the purpose of the EPA is right there in the name, Environmental Protection Agency. So it was, a Republican put it in, and every president since then, for the most part, has strengthened the EPA's mandate. So, if we're putting in less, and we would probably put in less iron than Woods Hole, than Loch Ness put in sodium hydroxide. But the question is always going to be, what are the effects? Can you control for safety? Are you being responsible? Because over the years, and the older you get, the more it happens, you'll see a product come out that gets recalled. And you can't really recall something from the ocean. And so we need to make sure that our science is on point. We need to make sure that our arguments are sound, and we need to make sure we have the science locked down tight.
So your help will be appreciated.
Yeah. We got Bruce and we got Ray. Julia.
How much oil food do we need?
There's actually a presentation about that later on by Captain Hugo Heinrichsen from the Chilean Navy. and he will talk about whale poop.
How much did Hugo pay you to ask that? I'm sorry. Ray?
So based on some of the previous questions, there was a figure of $1.3 trillion per year in support to some of these island nations.
Oh, not just the island nations.
Support for climate disaster support of some kind.
Mitigation and impact.
And if you look at our cost of $1 billion per year to restore the climate, that's 1,300 times less than this cost of support for the climate destruction. I asked Copilot to do another calculation, and I said, if we can remove 60 gigatons of CO2 for $1 billion, how many dollars per ton is that costing us? And that was a question asked earlier. And the answer is $0.0000167 per ton.
I hesitate to quote the ton numbers because they're speculation. The National Academy of Sciences and Engineering and Medicine published a report a few years ago, and I think there's a number in there like maybe it's in about $1 a ton. Whatever it is, it's substantially, you got to think about this relatively because we don't have a hard number. It's relative. Compared to direct air capture, which is energy and materials intensive, compared to mining a bunch of limestone to be able to put sodium hydroxide in the ocean. These are all expensive things to do, involve a lot of material, and we're talking about small amounts of iron. So think about it right now in relative terms instead of absolute numbers, because no one really has an accurate absolute number until we do more research.
All right. Well, if there are no more questions, I would like to thank you all for being with us for this first half of the day. I'd like you to invite everyone to come back after lunch, and I'd like to invite you all to invite people to come back after lunch. We have a couple more dynamic presentations. We're going to hear from our youth wing of the Foundation for Climate Restoration and also an independent youth organization, the Youth for Climate Restoration. And we're going to have a whole bunch more fun. I guarantee you that.
Thank you all.